In this second presentation, I really want to cover the concept of bone remodeling. Bone is a tissue that's alive. It changes over time depending upon our nutritional status and the stress that we place upon it. If we stress our bones, they get stronger, just like other tissues in the body. So this concept of remodeling really is key because we always need to be thinking about improving the strength of the bones of our body for our clients and our patients. So in this presentation, we're going to talk about that. We'll also look at the classification of different bones based upon their shape. And we'll look at a typical bone. In this case, we'll look at a typical long bone in the body and how it's structured. So the couple of cells, anytime you see the prefix osteo, that obviously should make you think of bone. There are a number of cells found in bony tissue, but these are the ones that are going to be the most important for understanding how bone functions and how it grows and remodels. Bone cells are going to begin with this prefix osteo, and we have osteoblasts, osteoclasts, and osteogenic cells. Osteoblasts, unfortunate name, I think of blast, I think of blowing up, but that doesn't work here. Osteoblasts actually build bone, and they are found on the superficial surface of bone. So in this picture, we can see, again, a long bone. Maybe this is a femur. And these osteoblasts, the cells that are going to basically create bony tissue, are going to be found on the outer layer of the bone, just inside the periosteum. Remember, connective tissues from AMP1, connective tissues are composed of cells, matrix, and fibers. Cells are obviously like osteoblasts, osteoclasts. In the case of bone, the matrix is going to be a very, not a lot of liquid, but a lot of minerals. That's what makes it a solid. And then the fibers that are found in bone are going to be a combination of collagen fibers and elastin fibers, with collagen fibers being in a greater amount, a greater percentage, which gives bone its tensile strength, but the elastin fibers give it some elasticity. And then the matrix, which is, again, a lot of minerals, is going to give it its density and add to its strength. So the osteoblasts are going to form this bone matrix and also contribute to the formation of the fibers that are found in bone. Osteoclasts are going to be found on the inner surface of compact bone, and they will basically help to maintain bone tissue, but also remove bone tissue. So they are going to remove the matrix over time. So the osteoblasts create it, the osteoclasts remove it. And then osteogenic cells are kind of these cells that can turn into osteoblasts or osteoclasts. So you start with this kind of this stem cell called an osteogenic cell, and then you will have the ability they'll differentiate into osteoblasts or osteoclasts. So the way that bone is kind of working is it's constantly producing new matrix with the osteoblasts and removing old matrix with osteoclasts. Bone remodeling is the term that's used, that's ongoing all of the time in bone. So this is again, the constant replenishment of bone by the osteoblasts and destruction of bone matrix by the osteoclasts. Remodeling, it occurs constantly, and the type of remodeling that occurs will change depending upon the stress that's placed upon the bone. So if the stress on the bone increases, so if you suddenly, you have a client, an elderly client who you've prescribed a walking program, and they didn't used to walk, but now they're starting to do more walking, that will increase the stress on the bone. That stress will encourage the osteoblasts to produce a more dense, a stronger matrix. And over time, that matrix will become stronger and more dense. If you reduce exercise, or you're an astronaut and you go up into space and you no longer have the effect of gravity, the stress on the bone decreases, and the opposite will occur. The osteoblasts will produce a matrix that's less dense, and the osteoclasts will remove that more dense bone that you originally had. So again, this is how bone remodels over time. It takes some time for this to occur. That's why it's really important for our clients, especially older clients, unfortunately, especially women that are at greater risk for osteoporosis. This is why weight-bearing exercise can be so beneficial, because it helps to maintain this bone density. Now, we can look at the bones and classify them in a number of ways. One way that bones are classified often is by shapes. We won't talk about this a lot in this class aside from this presentation, but bones come in a variety of different shapes, and that's how they can be classified. Long bones would include like the femur, the humerus. Flat bones could include the scapula, the sternum. Short bones are going to be again, sort of long, but not too long, and can include such as the cuneiforms, etc. Irregular bones just don't fit into a category. They're an odd shape and can include the vertebrae. And then finally, sesamoid bones. Sesamoid bones are bones that are basically encased within a tendon. In the case of the patella, it's in the patellar tendon, which is part of the quadriceps mechanism. This table comes from the online anatomy and physiology book that I really like from OpenStax. But again, it just classifies the different types or shapes of bones and gives, again, the different features and some examples of where these types of bones are found and what their primary function is. You know, a lot of the joints involve long bones, and long bones are great for producing leverage. Again, we talked about bones acting as levers. And again, if you wanted to move a heavy boulder, the longer lever arm you have, the longer stick you have to try to move it, the more mechanical advantage you have. So we do see, like in the lower extremity, long bones, and they are going to provide a greater amount of mechanical advantage, allowing us to lift larger weights and do so more forcefully and allow for jumping, running, etc. And again, we do see in some of the joints we have short bones, flat bones, and some irregular bones as well. But generally, the parts of the body like the legs and the arms that are really important for quick, fast, powerful movements, we see these long bones. But again, you could take a look at this table. It again gives some examples of each of the types of bone classifications and their advantage or function in terms of how the body may move. Now, real quickly, I wanted to go over kind of the structure of a long bone. Bones are amazing because they obviously are very strong, injured fairly infrequently, but again, they still do get injured, especially in athletics. And it's always a balance between strength and weight. You know, if we really wanted to have no fractures, we could make our bones very, very strong. They could be designed and filled with compact bone that's very dense, very heavy, and very strong. However, they would weigh much more. Therefore, it would take more energy to move around, and we would not be as quick as we are. So there is a balance between bone strength and bone weight. And we see that bone is structured in a way to try to be strong enough, but also lightweight enough. So when we look at this anatomy of this bone in particular, sorry, I lost my pen. I got to find my pen. We can see a couple of things. The shaft of the bone is going to be composed primarily of a type of bone that's called compact bone. Compact bone is very dense, very strong, and again is going to be what constitutes kind of the weight-bearing and the strongest portion of bone. So we see it in the shafts of bones. We see it around the periphery of the ends of long bones. And in a lot of short bones, they may be composed primarily of compact bone. Bone also has a region called that's made out of spongy bone. And we can see spongy bone, for example, here in the head of the femur. We have an outer layer of compact bone, but then we have an inner portion that fills basically the bone with this spongy bone. still made of a very strong, again, mineral-rich matrix, but it has these open pockets, these open areas that tend to be filled, obviously, with bone marrow. But that allows the bone to be strong, but also be a little bit more lightweight. So again, most of our compact bones are going, or most of our bones are going to be a combination of compact bone and spongy bone. In long bones, we also see some structures that are going to be important. We see one here, this line between kind of the shaft and the end of the bone. We also would see one down here at the bottom of this bone. That region is called the epiphysis, or the epiphyseal plate. Okay, the end of the bone is called the epiphysis. The line between the epiphysis and the shaft is called the metaphysis, and then the shaft itself is called the diaphysis. So the epiphysis is the end of the bone. The metaphysis is this line between the end, and the diaphysis is the shaft. In a person who's still growing, the metaphysis is actually filled with cartilage, hyaline growth cartilage, which is, in that person, it would be called a growth plate. So in a child, the metaphysis, that you can see that line there on this picture, is going to be, again, where the bones grow, where they grow in length, where they get longer. In an adult, a skeletally mature adult, that is now ossified and filled with bone. We also see in this bone, again, some regions of compact bone, some of spongy. The compact bone is dense and strong. The spongy bone is porous and does adapt in response to stress. So we will see that the spongy part of the bone will rearrange itself if we change our weight-bearing patterns. So most of the change of bone in response to the stresses we place upon it occur at these spongy ends of bone. And then, just as a reminder, the bones are where they articulate with other bones, such as here at the head of the femur or down here at the knee. The ends of bones are typically lined with articular cartilage. This is, again, cartilage that's basically glued to the surface of the bone, attached to the surface of the bone, but gives these bones a nice smooth edge. So we don't have bone rubbing on bone, we have cartilage rubbing on cartilage, which is much more smooth. We talked about the bone marrow before. Bone marrow tends to fill these spongy regions, and we have a combination of red bone marrow and yellow bone marrow. Red bone marrow is going to be the blood cell producing type of marrow. The term for blood cell production is hemopoiesis. So those cells are considered to be hemopoietic, which means they produce they have these stem cells that produce red blood cells, white blood cells, and so on. Red bone marrow primarily is found in the vertebrae, the ribs, the sternum, the pelvic girdle, and the proximal head of the femur and the humerus. The shafts of long bones pretty much are filled with yellow marrow, which again is a storage site for lipids that we can use for energy, so fat tissue. Well, this brings us to the end of part 2 of this series. And in the last series, what we're going to do is continue kind of in the same vein, but instead of looking at bone remodeling, I want to talk about bone growth, how bones change length over time as a person ages. And then we'll also take a look at how bone heals in response to whether it be full fractures where the bone is completely broken or stress fractures. I think understanding this really allows us to tailor our exercise programs to maximize bone strength and reduce the risk of injuries. We'll also spend a little bit of time talking about how bone changes over time, specifically how it begins to weaken as we get older, and how exercise can impact the rate of this loss of bone mass.